In this session, I'm talking about simple linear regression. We'll discuss the topic, the conceptual aspect behind it. Along with that, how do we really execute this simple linear regression in R? What are the kind of functions that we are going to use in R? And let's say once R gives me some kind of an output, a detailed interpretation of the output. So that is what we are primarily going to look at in through this particular session. So initially we will talk about, if at all I have to do a simple linear regression, what are the initial steps? What are the various ways that are available to me to understand the relationship between what we call as the dependent variable and the independent variable? What is that bivariate association that is existing between them? And once we execute this, executing it is not a big deal in R. Once I understand the conceptual aspect and primarily when do I use this kind of linear regression, what is the business background to it, if I try to understand that, running it in R is not a big deal. So once the R gives some kind of an output, how do I really interpret the output? What are the kinds of graphs that I can plot on the top of it? How do I interpret the graphs? And finally, we would spend some time in terms of understanding, is the kind of a model that we have built, simple linear regression model that we have built, is it really a good model? And how do I really assess the goodness of it, of that particular model? So this is what we are going to look at. For this purpose, I'm using one survey data that is typically being conducted at some kind of an amusement park, right? A survey data is conducted at an amusement park for the people who have visited this park. So let me just get that data. It is there as a part of my this particular location. So I'm trying to get that data. So I'm quickly seeing what is there as a part of that data. So I'll put up the head, right? Since I have taken that as a part of my variable called survey. So it is like this. So there are a few measures that are there. So something saying weekend, yes, no. So whether the group has visited that park on a weekend or not, or on a weekday. So weekend equal to yes means yes, they have visited on a weekend. Otherwise, they have visited on a weekday. The number of children that are there as a part of that group, 0, 1, 2, we see some kind of numbers. Then what is the kind of distance they have traveled to come to that particular place? So some of them have traveled a lot of distance, which is seen as 114. In some cases, the numbers are slightly smaller. Okay, the distance traveled. Then these are the different kinds of satisfactions that we have captured. For the rides, what is the satisfaction level? For the various games, what is the satisfaction level? For the waiting times, regarding the waiting time at the park, what is the level of satisfaction they carry? Then the cleanliness of the park, what is their rating regarding the cleanliness of the park? And finally, what is their overall experience? So these are some of the information that have been captured, right? So that is what is our data. We will try to do a simple linear regression in terms of trying to understand the relationship between a dependent variable. Here I'll take the overall satisfaction as a dependent variable, right? Overall satisfaction, I really want to link it with, let's say, some kind of a satisfaction, let's say games related satisfaction. So depending on the level of games related satisfaction, can I try to understand the overall satisfaction of the visitors? Or basically based on the, can I really predict the overall satisfaction of the customers based on the kind of satisfaction they carried with the games? So that could be a kind of a motive for this particular session. So initially, once I have loaded the data, Look out for the summary. That's the first step as a part of any exercise. Take the summary of it to see if there are some abnormal things as a part of the data. Right, I'm looking at the survey. Okay, weekend looks like there are 259 people who have not visited on a weekend, but 241 have visited on a weekend, more or less equally balanced. So there are a few teams which came up with 0 children, but maximum of 5 children are there in the group. So the distances are anywhere from half a kilometer to 239 kilometers. So that's a kind of a widely varying kind of a distance altogether. Then the kind of satisfaction they carried for rides is anywhere between 72 to 100. For games, it is between 57 to 100. Regarding the waiting times, I see that some of the people have given much lesser scores, 40 to 100. Regarding the cleanliness, looks like a lot of people have given much decent scores, going from 74 to 100. And but overall, there is something alarming. The minimum looks like 6 and the maximum is 100. So yeah, probably this could be an outlier, but yeah, we have to really check out before we take any kind of the next steps on the top of it. So this is what is my first step. As a part of the initial step, before I go ahead into the fitting of the model, I can try to understand as a part of this particular activity. Then the next thing I suggest is look out for the distribution. So we have discussed earlier that G pairs is a much better function, especially if I'm having uh, binary variables or probably categorical variables, right? Factors as a part of my data, then it's better to use G pairs rather than using the scatter plots where I use scatter plot matrices. Instead of using the scatter plot matrices, I using the pairs function, I can rely on the G pairs function. This is much more elaborate. This is what we have discussed earlier as well. Right, so let's use the G pairs function. So G pairs function is present as a part of the G pairs package. So let me load the G pairs package. Right. So on that I'll use the G pairs function, wherein I'm linking survey as my input variable. So I could see that this is the G pairs function that has been created. These are the graphs that are associated with the G pairs. So across the diagonal, I am seeing histograms. So I could see here it is weekend versus weekday, number of children. This is a discrete, right? With respect to distance, probably there looks like a lot of skewness towards the right, right? You see a whole chunk of values towards the left, but towards the right there is nothing much. So there is a kind of discreteness that is present, which means there could be a lot of positive skewness in the data. Rides, games, wait times, cleanliness overall looks like some kind of a normally distributed. So I may not be interested in touching those things, but probably because the distance is looking pretty much skewed, I can very well go with the understanding of transforming it, right? So because this is looking pretty much skewed kind of a data, but otherwise also I can quickly check out the descriptive from the psych package. I can check out for the descriptives as well. So let me load the psych package, and on that I'll take the describe of survey, wherein I could see here, okay, weekend I can ignore, number of children also let me ignore, but distance, the skewness is looking like 2.57, very much positively skewed, and kurtosis is also 9, very much away from 0. But if I look at other things, For rights, skewness is pretty much okay. For all these things, it's very close to 0, which means it's not positively skewed or negatively skewed. The same goes with kurtosis also. The numbers are pretty much around 0. Only the distance is looking pretty much with a very high skewness and very high kurtosis. Now this is where it's better that I replace or readjust the data, wherein I add, instead of distance, I add log distance. I do some kind of a transformation on the data and I create one new column. So let me call it as survey $ln dist. That is what I am calling as a log distance. So where I am taking the logarithm of survey distance. So I am taking the logarithm of the distance and I am adding it back to survey. Now once I have done this, let me see now the descriptives of the survey. Log distance is one more variable that got created, whose skewness is pretty much fine, whose kurtosis is also pretty much fine. So overall it looks like this is very much comfortably normally distributed, whereas the original distance was not. So this is what we could get just by looking at one, the G pairs, or quickly running the psych package, where you are running the describe function on the top of it. So we have checked whether each individual variable has a reasonable distribution, which is what we are calling as close to normality. Then I can also check for joint relationship among the variables. Right now, pairwise we can look at for the relationships, and there my intention is to see whether the variables are more and more appropriate for modeling. And what I really need to understand is all these scatter plots, the more and more elliptical they are. So here you could see it's an ellipse, it's an ellipse, it's an ellipse. The more and more elliptical they are quite comfortable for modeling purpose. Whereas means a linear model can quite comfortably be used to model them. But if you see here with respect to distance, it is not looking elliptical. So there is a problem with the distance. Let me try if the same case holds for log distance as well. Now if I see with respect to log distance, it's fine. Looks like a lot of centeredness, right? Compared to this particular graph, which is completely cornered. It is not, it's in the center. Probably it's looking like a circle, but at least it's a kind of a distribution which can be modeled through. It's a kind of ellipse expanded into a circle, but I can still look at some kind of linear model for that kind of a data. So a few things, if any variable is highly skewed, in our case distance was highly skewed, I have done the appropriate transformation. Right now I have done the log transform, but I could have tried the kind of generalized Box-Cox transformation as well, where any other value of the lambda is very much possible. And when I am looking at correlation between them, they may be highly correlated with one another. See, majority of the times here you could see very high correlations that are existing between the variable. Now if that's the case, the very common thing that you can think of is, see, people when they are giving their ratings, they get biased. Their overall experience will get translated into individual item-wise experience. That is what we call as the halo effect. Majority of the times when you are giving these kind of survey questions, the individual elements that you have given as a part of the survey, they try to give a rating based on what is the overall feeling they have about this particular experience. So sometimes if they got a very good experience, irrespective of what the detailed questions are, they tend to mark higher ratings for every question. But if they are dissatisfied, suddenly that can get translated into the worst for all the questions. So it is very difficult to assess. If at all that kind of halo rating is very, very heavily seen in the data, then individual effects cannot be easily distinguishable. So just to understand that particular part, I am using the correlation and core plot mixed packages functions to investigate if there is to actually get the kind of numbers, much appropriate kind of numbers, to really see whether such kind of exactly ones kind of correlations are present. If exactly one kind of correlations are present, there is no way that I can test for the individual implications of the data. I may have to remove a few of those variables there. So that's where I would try to load my package core plot. Core plot package is what I have loaded, and there first we'll find the correlation. So here what is that we'll take? Will not take the weekend. We'll take all of them, will not take the distance. So this is 2, 3, 4, 5, 6, 7, 8, 9. So I'll take 2 to 9, right? But without the 3. So this is what is the kind of correlation I would like to take. So let me take core plot dot mixed. When I say mixed, I'll get in the upper part, I'll get the correlations in the form of circles, ellipses, etc. And in the lower part of this matrix, so which means in the upper part of the matrix, I'll get circles and ellipses. And in the lower part of the matrix, I'll get their numbers. So I'll take the core plot dot mix. As we have discussed earlier, the input is the correlation. So I am taking the correlation of this survey data, wherein I am taking all the rows, but the columns I am taking the second column and 3 to 9th column. These are the columns I am not taking 3, I am taking 4 to 9 because I don't want the distance column. So once I did this core plot, okay, I have to close the bracket. One more bracket is there. Yeah. So this is the kind of a correlation plot that I am getting. Right. So these are the numbers that are coming out. Rights versus cleanliness. It looks like 0.79 and 0.32. 0.46, 0.59. So these are the kind of correlations that are existing. So there are a few that are existing out here, right? Number of children versus overall is looking like on a higher note, right? So these are some of the things. So by default, it's a kind of a circles, but the same logic, if I take it saying upper equal to ellipse, the same things would be plotted in the form of ellipse. So we have discussed about this chart earlier. Okay, I have to finish off the core plot first. So mixed correlation is the input and upper is ellipse. So this is what I am getting, right? With respect to log distance, the numbers are pretty light. Whereas with respect to number of children also the numbers are pretty light. So I could see that though the correlations are existing, they are not that significantly high that the overall rating is influenced by each one of them. If I look at overall, there are in 0.6s and 0.5s kind of numbers. So which says that it is not that serious kind of a problem. I can very well go ahead in terms of doing the modeling. If one of them are nearly identical, we can proceed further. But if majority of them are coming more and more identical, it's better to remove a couple of those variables before we get into our modeling exercise altogether. So that's one thing. That's the initial step that we are looking at. And once we have completed that initial step, we are now moving forward in terms of understanding the bivariate association between the variables. Now let's say this is the question I want to frame. I want to look at the relationship between the overall satisfaction versus the satisfaction with respect to games. So I want to take overall satisfaction versus the satisfaction with respect to game. So this is where I'll try to do a simple plot, right? First basic thing. So I'll look at overall tilde games. This is what I want to take from the data which is survey. So from this data I want to get this overall plot, overall versus the games. So it looks like this is the kind of games versus overall plot. I can set the x-axis labels, y-axis labels, so you know by now how do you set all these things. So I'm not going more into it. And this is what is the kind of scatter plot that we are seeing initially. Now I have to proceed further. So it looks like there is a kind of an increasing kind of a relationship as the satisfaction of the games is increasing. Looks like overall satisfaction is increasing because there is a kind of upward sloping kind of a graph that we are seeing. Then the next part that we are looking at is how do you get into a linear model using a single predictor, which means I am trying to model the overall satisfaction taking the games related satisfaction as the input. So it finally comes out like overall satisfaction is equal to some A plus B times the games related satisfaction. This is what is a simple linear model. So I'm trying to model the overall satisfaction by taking the game satisfaction as the input. So it is estimating a best fitting line through the cloud of points. So across all these points, one single line, straight line, that is best fitting. That is what we call as the linear model. When I say best fitting, the error from all the remaining points is the minimum most possible. That is what we call as the linear model. So we can typically execute the linear model using this lm function. So let me take this lm where I'm talking of overall tilde games. This is what I'm finding out as the lm, and data I'll take it as survey. So this is my lm function wherein I am getting the equation like this. So my intercept is, right, there are two inputs it is giving. Intercept is minus 16.0117 and games it is saying 0.8551. These are the two numbers which are very important for us. So this is what is the output that is typically given by my lm function. Now I can really check out for the output, right? So this is what it gives. So it is giving me the formula that I have written. lm, the formula is overall tilde games and the data is survey. So based on this, these are the values that are typically computed. So in the output, this is what, and if I typically want to get a best estimate of the dependent variable based on independent variable, then I'll use this formula. Let's say someone has given a game satisfaction as 60. Then the way I will get my overall satisfaction is minus 16.0117 plus 60 multiplied by 0.8551. So whatever is this number, this is the number that we allocate for the estimate. That's the best estimate of the overall satisfaction that we can give based on the satisfaction for the games. Now that is the way we understand the bivariate association between the variables. Now when you typically simply do lm, right, this is what is the formula that we have got. Now I can save this entire output into one single variable. So probably I'll call it as model 1, and this lm output I will try to save this to this model 1 so that I'll use this model 1 wherever possible. So probably now the same, we have this plot. Let me again redo the plot here, right? Let me redo the plot. So this is the same plot. To this now, if I want to add this regression line, I can add it as AB line. I want to add this regression line, the smoothened line. I'll add this AB line saying model 1, AB line model 1. I want to put some kind of a color of my choice. So if I put a red color to this AB1, it says that it draws a kind of a line. AB line is typically being drawn by completing the LM part of it. It does a linear modeling, and based on that linear model, whatever is the A and B values, intercept and the slope values that have come, based on that the smooth AB line is typically being drawn. So I can add the linear fit line to the scatter plot. That is what I have done. Now even the entire object, whatever the model has given, if I want to understand what all output did the model give, did LM function give, I can do the STR of model 1. Now these are all the calculations that it has done. If you see here, it has given me the coefficients. So these are my A and B values. It has given the residuals. We'll talk about them. It has given the effects. It has given the rank. It has given the fitted values. Some of the things. These are all the different kinds of calculations that it has done, and it has given them as a part of the output. Now if I really want to get the coefficients, I can simply say model 1 dollar coefficients. Right, if you see here, model 1 dollar coefficients, I'll get the intercept as well as the games part. So I can simply get, just like for every model, I can even run a kind of a summary to get a complete summary of my model. Right, that's more important. This output interpretation is very interesting part here. This is the summary of the linear model. So first part, at least we are clear. It's a linear model. It's a formula. Overall is my dependent variable. Games is the independent variable, and the data is the survey data. So that is what is the first thing that this model is presenting. But apart from that, we can see there are a bunch of other outputs that are coming up. So that is what goes as a part of the detailed output interpretation of the model. We will look at that now. So now let's move on to the detailed understanding of the output. So the first part in the output I want to talk about is the coefficients part. So this part we have already seen, right? The coefficients are intercept and the slope per game. So the intercept part is minus 16.01173 and the slope is 0.85513. So these are given under the estimate part. These are the model coefficient. Now what it means is, if the game satisfaction, if I look at this as the input, if the game satisfaction increases by 1 point, I see that the overall satisfaction will increase by 0.85 points. That is the typical relationship between these two. That is the meaning of this slope. Right? Intercept is negative. In this case has no meaning, because it means that if the game satisfaction is 0, then the overall satisfaction is minus 16. But there is no meaning to it. In some cases, the intercept does not carry any kind of a meaning. So I can very well ignore the intercept from my analysis altogether. But on the other side, see, generally, if I take the slope into consideration here, if the game satisfaction increases by 1 point, I'm saying that on an average, I see that the overall satisfaction is increasing by 0.85 point. That's what we interpret from here. Then we also will look at the standard error 6.22 and 0.07. So very interesting thing to understand. It's the uncertainty in the coefficient estimate. So it's like my coefficient that it has computed, there is some level of uncertainty to it because it's a sampling exercise that we are doing, right? So there is some level of uncertainty in the estimation of the coefficient. If the data changes a little bit, then my coefficient also could change. So what is the typical concept is, I assume that the whole data is a random sample. Whatever the data that I have taken is a random sample of a larger population, and based on that, if the sample keeps changing, I would like to see what is the kind of coefficient that is coming out to it. And that kind of uncertainty, there is some kind of variation that is there to that coefficient, and that uncertainty is what we call as the standard error of that particular coefficient. Now the t value, the other thing that is computed here, it's simply computed as the estimate divided by the standard error, right? So which is talking of how many times the uncertainty value is the value of the estimate. Estimate as a proportion of the standard error. That is what is the t value that is computed. So in this case, it is like 0.85 divided by 0.078, which works out to 10.86. So that's the t value. Then there is a p value, which is the probability. If I take this t value onto a t distribution table, what is the probability that what is the area under the t table comprising of this particular value? So that is what we are taking as the p value, or the probability greater than or equal to t. So the p value is nothing but, in R, it is represented as the probability greater than or equal to t. And this value in general is the probability that the null hypothesis is true. So in this case, the null hypothesis for each of these coefficients is, each of these coefficients here, the coefficient b, I am taking it as 0. This is my null hypothesis, and the alternate is b is not equal to 0. So I will look at the p value. So here the p value is 2 into 10 to the power of minus 16, which is less than 0.05. So my decision will be in favor of the alternate hypothesis. And the alternate hypothesis is the coefficient is not 0. So the whole thing is the test that is being performed. I look at the p value of it. If the p value is less than 0.05, my decision goes in favor of the alternate hypothesis, which assesses that the coefficient is significantly different from 0. But if the p value comes to be greater than 0.05, then I will not reject the null hypothesis, which can tell me that the coefficient is not significantly different from 0.05, significantly different from 0. So which means that particular variable does not have any kind of an influence on the dependent variable. And similarly, we can also get a 95% confidence interval estimate also. Right, I can take the confidence interval conf int of my model 1. So which says this is the 95% confidence interval. If I am taking for games, it means that though I have got the coefficient as 0.855, if I repeat this exercise with different kinds of data point, the games, the coefficient could be anywhere between 0.7 to 1.0. Right, there's a 95% chance that whatever may be the data that is changed, the confidence interval would be anywhere between, the coefficient could be anywhere between zero point 0.7 to 1. It cannot be less than 0.7. Very, very rare chance, limited chance that the coefficient could be less than 0.7 or greater than 1. So it is very much different from 0. That is what we can assess either through the confidence interval. If the confidence interval contains a 0, then I cannot reject the null hypothesis. If the confidence interval contains a 0, then I will not reject the null hypothesis. But if the interval does not contain a 0, like this, it is 0.7 to 1. So if it does not contain a 0, I can very well reject the null hypothesis and take my decision in favor of the alternate hypothesis. And the traditional estimate is whatever is my coefficient, I'll take it as 1.96 times the standard error on either side. So here the standard error is 0.078. So these are computed as 0.85 plus 1.96 times the standard error, which gives me 1.00. 0.855 minus 1.96 times the standard error will give me this. So that's a traditional computation of the 95% confidence interval for the model. Then, so now that we have understood the coefficients part in detail, now we can move on to understanding the residuals part. The residuals, they typically tell me how closely the data is to the best fit line. So when this line is typically being drawn, these differences, right, from here to this line, from here to this line, from here to this line, these are all the residuals. So these residuals tell me how closely the data is to the best fit line or the regression line. So basically it is the kind of a difference between the point that is predicted by the model versus the actual. So the difference between this and this, between this and this, between this and this. So when I draw a vertical line from each of the points to that line, whatever is that distance, that is what we are calling as a residual. In some cases the residuals are positive, in some cases they are the negative. So I can very well look at the quantiles of the residuals, especially the quartiles which it has given here regarding the residuals. The minimum value is minus 43, the maximum is 41, and the first quartile is around minus 9, the third quartile is around plus 9. So I could clearly see that the quartiles are pretty much symmetric, minus 9 to 9. So the more and more the quartiles are symmetric, I can very well understand that the overall distribution of the data is pretty much symmetrical in nature. And there are some extreme outliers, there are some extreme errors, 40 minus 43 and plus 41 kind of stuff. So I can really look at even those kind of quartiles for each one of the residuals. Right, I can very well look at the quartiles associated with each of the residuals. So let me take the residuals. I can take model $1 residuals. If I take that, I get the list of residuals for each of these values. Now there are a kind of different kinds of plots that I can do on the residuals as well. But let's understand. So I am first verifying the quartiles of the residuals. If the first quartile and second quartile are more or less around 0, when I say around 0, equal distance from 0 approximately, then I can say that the overall, the symmetric nature typically exists. Then the other important area that we should look at from our model is the last portion, which is primarily talking about the model fitment. The first part, the residual standard error. In this case, the residual standard error is 14.29. Very important measure for our estimation purposes. So it's a estimate of the standard error of the residuals. So I have taken the residuals, right? These are the residuals I have shown. So if I simply take the standard deviation of my residuals, model $1 residuals, if I take the standard deviation of those residuals, which is what I've got 14.28 or 27, more or less similar to what we have got as the standard error here. So the standard deviation of the residuals is what is the standard error of the estimate. And the way we are interpreting it is, when I am trying to do some kind of a prediction, on an average, my error in prediction would be in the range of 14.29. So on an average, the error in prediction will be around 14.29. So my objective always will be to reduce this kind of an error, because the more and more the error that is existing, my prediction accuracy is typically going low. So my prediction interval is getting wider. So this is where my intention is always to minimize this kind of a number. Then the other input that we are looking at in this context is the R squared. Here the R squared is saying 19.14%, right? Which says, see how much variation in the dependent variable. Now this is my dependent variable, which is the overall satisfaction. The dependent variable is varying. The variation in the dependent variable is this much. Whereas when I have done a predicted model 1, I look at the variation in the predicted model, it is only this much. So what we are trying to say is, how much of this total variation in the data is captured by my predicted model. That is what we are calling as R squared. So which means this variation divided by this variation is what we are calling as the R squared. If I have to demonstrate that to you, let me take the variation of the original data, right? Let me take the variation of the original data. The original data is survey dollar, right? The variation survey dollar overall. I'm taking the variation in the original data, which is 252. I'll take the variation in model $1 fitted values, which are the predicted values. If I take the variation of that, it's around 48. And if I take the variation of the residuals, model $1 residuals, it's around 203. Now look at a few things. This value plus this value, 203 plus 48, approximately is equal to this 252. Right? So the total variation in the data is the summation of the variation in the fitted values plus the variation in the residuals. So I am trying to always look at what proportion, what portion of the variation in the overall data is taken care by my fitted values. So if I look at that, if I take the ratio of these two numbers, right, this number fitted values variation divided by the variation of the overall, so that is what is coming out to be my R squared, which is what is given predicted by my typical data. So this is what is the R squared interpretation. How much variation in the dependent variable is captured by the model. The higher it is, the better it is. Then the next part that we are looking at is the F statistic. In this model, the F statistic is being shown as 117.9. So this is a statistic, it's a test which is doing whether the model predicts the data better. So which is talking about the goodness of fitment of the model. Whether the model that we have chosen, the linear model, it predicts the data better compared to taking the simple average of the outcome variable. See, if the model is better, I'll put it as, so it's as like this. My model is y equal to a plus bx. Now, if the model is nowhere better, it's as good as saying b, I'll put it as 0. So it is y equal to a. So the predicted value is just a constant. And that constant is what we are calling as the average of the values. So if I take the average as the better estimate of the model, or the model that we have taken is much better than just taking average as an estimate for the data. So that is what is the F statistic saying. So whether our model is better than a model without any kind of independent variable, right? By how much extent is our model, which we have taken games as the independent variable, is better than a model in which no independent variable is taken, just the average of the dependent variable is taken as the predictor for the future. Now that is what is provided by the F statistic, and here the p-value of this is very important, which assesses the overall fitness of the model. The p-value is 2.2 into 10 to the power of minus 16 less than 0.05. So my decision is in favor of alternate hypothesis. So in this case, the null hypothesis is the model is not good. Right, the model which we have fitted is same as a model where no predictors are there. Right, it's more or less similar to the model even without considering any kind of predictors, which is like the simple average of the data is nowhere a worse model compared to the model that we have created. But the alternate hypothesis says yes, this model is better than just taking a simple average of the values. This model is quite better than that. So that is where the alternate hypothesis comes. So p-value less than 0.05, then probably I am rejecting my null hypothesis and my decision is taken in favor of the alternate hypothesis. So I can very well say in this case that the model without the predictors, right, is nowhere closer to model which we have done here with the predictors. So the model that we have considered with one predictor is better off compared to a model with no predictors. So that is what is the output that is typically provided by this model talking of. Alright. Then one more important aspect that we are doing in this context is checking the various ways in which I can assess the fitment of the model and the adequacy of the model. So I will have to really check, is this model correctly fitting to the data? Is this model more and more appropriate to the data? So from that perspective, we need to really understand some kind of assumptions when we are fitting some kind of linear model to any kind of a data. So there are a few assumptions that are made when we are using this LM function to fit a linear model to the data. So the first assumption is this model assumes that the relationship between the predictors, what we are calling as the independent variables, games in this particular case, the relationship between the predictors, which is the games in this case, and the outcomes, which is the overall satisfaction. Right? The relationship between them is linear. It is making an explicit assumption of that. But in reality, if the relationship is not linear, then the model will make systematic errors. There is a possibility that it says there is no relationship between the data, Whereas there could be a very strong non-linear relationship that is present. So we have to really understand whether this relationship is more or less linear. Only then I should be able to use this LM model. So this model does not consider the curvature or some kind of a non-linear relationship existing between the dependent and the independent variables. And the parts of the other major assumption that it makes is the parts of the data that do not exactly fit the model, which are the residuals. It assumes that the residuals are normally distributed. So I can very well check the describe of the residuals to see whether they are normally distributed or not. The site package is already loaded. So I can look at the describe model $1 residuals to really see whether the residuals are normally distributed or not. Skewness is 0.2, very much close to 0. Kurtosis is minus 0.6, very much close to 0. Either I can do that activity or I can very well go with Shapiro.test, which is a proper test to check the normality. So I can take model 1.residuals through the Shapiro test. So the p-value is coming out here 10.46%, greater than 0.05. So my decision is in favor of the null hypothesis. So in this case, the null hypothesis is the data is fitting a normal distribution, whereas the alternate is the data does not fit a normal distribution. So in this case, I go with the null hypothesis saying that my data, which is the residuals in this case, it is fitting a normal distribution altogether. So parts of the data that do not exactly fit, they should be normally distributed. That is what is one more assumption of this model. If that is not the case, right, then I should look at some kind of transformations or some such kind of stuff, removing the outliers, some such kind of stuff before I go ahead in terms of building and fitting the model, right? So I can either get the plot of it. One, I have done this two things to check for the normality. I have used the describe function, or I have done a Shapiro test, or probably I can do a simple plot of the residuals as well. So it's looking more or less scattered, no concentration at any particular point in time. So it looks more or less kind of scattered kind of thing. So they are very much random in nature. Now the other part that we can really go ahead in terms of interpretation from this model is the overall I can go for a diagnostic plot. So in R, when you are doing a plotting of your regression model, you get 4 different plots, right? These 4 plots, they assess the fitment of the linear model to the particular data. So I'll take the LM object and do a plot. So I can simply do a plot. LM object is already saved in model 1. So I'll do a plot of model 1. Yeah, it's better that we take all 4 in one single graph, because it's they'll show all 4 functions here, right, rather than taking it like this. So let me first get all 4 here. We can use our par function, right? The par function where we are setting mf row equal to c2 comma 2, so which sets 2 by 2 kind of a page. So based on that, I'll do a plotting of model 1. Once I set that, I'll do a plotting of model 1. So there are 4 different plots that have come up here. So the first plot, right, we'll go with the first plot. It's a plot between residuals versus the fitted. So the fitted value is taken here. The residuals are typically taken here. So here it looks more or less scattered, right? It looks almost scattered kind of stuff. There's no centric somewhere. So there's no obvious pattern. So residuals, it means that the residuals are more or less due to a random error. If there is some kind of a pattern, then it means the residuals are not so random in nature. So there has to be some kind of variable that needs to be introduced which will capture the residuals. So the first point, when I'm looking at my first graph, so I'm looking at the fitted values versus the residuals. If there is no pattern, it means that the residuals are primarily due to random error and the model is very adequate. Otherwise, it says that the model is not adequate. I have to look out for some other kind of a model. Then, when I come to the plot 2, which is the one below it, scale location versus the standardized residuals, square root of the standardized residuals. So here, the raw residual value is not taken, the minus and plus. It's a square root of the standardized residual is plotted. So standardized residual is I'm actually taking the distance of that residual in terms of standard deviations. So I'm taking only the positive standard deviations here. I'm not taking the negative standard deviation. So I'm taking the square root of the standardized residual. So if there is some kind of pattern, here also there is no pattern altogether. But if there is some kind of a pattern in the residual, then I can say that the relationship is more and more non-linear. I cannot use the linear model to model this kind of a data. So if there is some kind of a pattern that is coming up, right, when I am doing the fitted values versus the square root of the standardized residuals, if some kind of a U-shape kind of a pattern or some kind of a wave kind of a pattern is appearing, then I can very well say that the data is having some kind of a non-linear relationship and the linear model cannot be used to fit that kind of a data. And if there are some kind of residuals that are present which are very high in nature, which means like an outliers, they are typically numbered. Now if you see here, there is a number 156, there is a number 129, 57. These numbers are typically highlighted by R saying that they are outliers. So it's better that we handle these outliers. So that's one more information that we get from this particular graph. So if I see some kind of a cone shape, something like this means there is a kind of a non-linearity that is present in the data, because as the fitted values are going on either of the directions, the errors are typically increasing. The standardized errors, they are typically increasing, which is what is an indication of heteroscedasticity present in the data. So for some kind of fitted values, the errors are much narrower, but as the fitted values are going wider and wider from a particular range, I see that the volatility is increasing, which means the errors are becoming more and more wider. Even that can be made out typically from our plot 2. Then looking at plot 3, this is a straightforward graph which is a normal QQ plot. So it checks whether my fitted values or whether my data is fitting a normal distribution properly or not. So the residuals which we have taken, are they following a normal distribution or not? So I am taking the actual residual versus if that particular residual is normally distributed, what should have been its theoretical quantile. So I am looking at the theoretical quantiles as well as the standardized residuals, going with a plot. So as long as these points are above this 45, on this 45-degree line, it indicates that all these residuals are normal. The more they are deviating from this line, it indicates that the residuals are not normal. And probably if you are seeing some numbers being highlighted, especially 129, 156, 57, these are the elements that are highlighted by the graph saying that these are typically not normal, right? They have some kind of exceptional behavior. So it's better that we first understand those variables and those records, and if required do some kind of removals or some such kind of records, because they are being highlighted as outliers by our model. Then the plot 4 is primarily for identifying the potential outliers in the data. The outliers again are identified with numbers, right? So they are the ones that are unduly influencing the fitted line. They are influencing this data quite heavier. So that is where we are trying to understand those outliers and if possible handle them. So this goes with the concept of leverage. Each point is considered given some kind of a leverage. All the points, if I see, each point is given some kind of a leverage. And this leverage is typically computed based on the Cook's distance. The Cook's distance is nothing but how much influence the point has on the model coefficients. It talks about this one single point, what is the influence that it has on the coefficient of the model. So which is as good as saying, if I remove this one single point and based on that recompute the model, the coefficients will change. Now what is that change in the coefficients that is occurring but just by removing this one single point? If the coefficient is changing quite heavily, then it means that that particular point has a lot of influence on the model. But if the coefficient hardly changes, then that point leverage is much lesser. This point does not have any kind of a major influence on the coefficients at all. So that is what is the Cook's distance. How much the predicted value would change if the model is re-estimated with that point eliminated. I just eliminate that one single point, recompute the coefficients, and based on that do a predicted value. If at all there is a big change, means that that point is influencing heavily, and if the change is quite narrow, the point has very smaller influence on the overall model and the coefficients of the model. So any point that is having a very high residual is more like it's an outlier, and high leverage, both of them to be higher. So we are plotting between the leverage and the residual. Any values that are having high residuals and high leverages, they are a very big outliers. That one single point is having both a different pattern from the rest because the residual is higher, and it is also creating a very high undue influence on the model. So those things that are coming somewhere here in this range, they have to be handled quite comfortably. They have to be handled very, very effectively because they are going to have some kind of undue influence on our model. Those are the ones that are reflected by their numbers in R. So the point number 55, point number, some of these things, probably if we widen the graph, we can get much more clarity here, right? There is some number ending with 3. So these are the points that are highlighted by R, saying one, they have an high undue influence, and two, they are following a different pattern. So those difficult points have to be really inspected as per outliers, and based on that appropriate actions need to be taken. So it's better that I identify them, but yes, if I want to identify, I need to get the values. But let me try for this 55 just to inspect it. I'll say survey, just to inspect this number 55. I'll simply take the survey where I am taking the row number 55. Probably let me take even these which are coming on the higher side. 57, 129, 156. So these are the numbers I would like to take, and all the columns just for doing some quick inspection. Okay, so there are some weekends, so probably let's see here. The overall ratings are 7 and 6 for these numbers, right, which are pretty much on the lower side. But with respect to games, it looks more or less okay. But I think this overall satisfaction of 7 and 6, whereas in this case it is 100. So probably this could be the reason why these numbers are coming out more heavily here. But yes, if I want to really understand this and if I want to delete some of these records and redo the model, that is very much that is possible. But what I generally suggest is do not omit the outliers unless they really are very, very obvious errors in the data and they are having a very, very significant influence on our result. We don't need to really omit the outliers. So we can very well work out this way and try to understand any kind of simple linear models that are coming out in our data. So that is what I wanted to talk as a part of this session. We talked about the initial steps that we need to do when we have to do this modeling exercise. Then we are fitting a bivariate association through different mechanisms. We have fitted a linear model, try to understand the output that is given by R as a part of that linear model. And finally, we have some kind of ways in terms of assessing this model fitment through the numbers way as well as through the graphical way. So we have spent some kind of time in terms of understanding that relationship as well. If you have any further queries, you can very well get in touch with me by giving me a call on this number, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.